Okay, so welcome. We're finally ready to apply all of that machinery, and we'll apply to cosmology. Here's what we're dealing with. The universe. Notice that those bright spots are not stars, they're galaxies. Each one of them, it's part of Hubble deep field, one of the deep field analyses there. We're peering billions of light years into the universe there. Now, when we apply quantum field theory to cosmology, then we'll deal with a non-trivial background space-time. And if we took the actual space-time, even if we knew it, in all its details, it would be hopelessly difficult to do quantum field theory on that space-time. So we will need to do some approximations. And we base those approximations on observations. A key observation is that even though those galaxies locally cause curvature, once you're looking at scales of like 1 billion light years or larger, then the universe turns out to be spatially flat with an enormous accuracy. I'm not talking 10 digits behind the comma, but like 1 digit. So it's that's remarkable that it's neither positively nor negatively curved as far as we can tell. There's no evidence for either way. It's pretty much flat, which means that if you took a huge rectangular triangle, then Pythagoras would apply, and the sum of the angles would be 180 degrees. For some reason, and we will discuss one of those possible reasons, the space-time is very flat at large scales. It's a prediction of cosmic inflation that we will cover in this course. But for now, let's just take it as an observation that it is spatially very flat on sufficiently large length scales. And another observation that's independent of this one is that the cosmic expansion is also apparently, according to observations, very isotropic. So the universe is expanding all right, but it's expanding in each direction at the same rate, and has been expanding in each direction at the same rate. Remember that we see back into the past as we look very far away, so we actually also have evidence about the time evolution of the isotropy. Given this evidence, we will model space-time as Friedmann, Robertson, Walker, sometimes also Lemaitre space-times. Sometimes that name is included. The simplifying approximations are space-time is modeled as having no spatial curvature at all, and also that its expansion is entirely isotropic. You might think that, well, yeah, that's a good approximation, but it turns out that because the Einstein equations are nonlinear, you can have rather counterintuitive features. Unlike for a regular theory that would be linear, like quantum field theory, it turns out that the Einstein equation has highly non-trivial solutions. There are solutions that have been studied which are coming very close to a flat universe that's almost isotropically evolving, but only temporarily. And then it takes off and does all sorts of weird stuff. So a phase of flatness, of almost flatness and almost isotropy can arise temporarily. And that's a bit weird. But this is what you get with nonlinear equations. This is also the reason why perturbation theory is really a non-trivial thing for general relativity. It seems that with the full page view, what is this? Why? It takes the entire page. Yeah, it takes the entire page. Yeah, but then where's the next page button here? Page down. Yeah, that's what I'm trying, page down, but that's not what's working. Okay. It needed the control as well. Okay. Okay, well, it just fits on the screen, isn't it? So with these assumptions, we choose, with these approximations, we now choose a suitable coordinate system. We will later tweak it a little bit too, but for now we start with this coordinate system. We need a time coordinate, and then we need space coordinates, and we choose them carefully. So as for the time coordinate, let me start with definitions before I define the time, some useful definitions. The motion of galaxies is mostly due to the cosmic expansion. If you take two galaxies, like our galaxy and a galaxy far away, then then what? Oh, quite amazing. What? It doesn't. Oh. Okay, go down here, and then we try this. Yes. Okay. So galaxies move away from each other. Two galaxies that are far away from another will move away very fast from another. And that is called the Hubble flow, that galaxies drift away from each other, each galaxy from every other galaxy. That's the Hubble flow. That's the definition of the term Hubble flow. It's the motion of galaxies because space itself is expanding. Now, in practice, however, galaxies don't exactly follow the Hubble flow. For example, our galaxy, the Milky Way, is not, because it is in a dance with Andromeda. Andromeda and the Milky Way are approaching each other. And that means that on top of the Hubble flow, on top of moving away from all other faraway galaxies, on top of that, they also have this inspiraling that going on, that they are attracting each other. And that kind of motion is called peculiar motion. So galaxies have on top of the Hubble flow also peculiar flow, which is with a peculiar velocity. And these velocities are generally very small compared to the velocities that you get between galaxies that are far away from another. Now, using those definitions, we will define as the time coordinate t the proper time of a freely streaming observer who has no peculiar velocity. So imagine a galaxy that has no peculiar velocity, and in it an observer that's sitting in the middle of it, no peculiar velocity. It could be you as an astronaut somewhere in intergalactic space, not having any peculiar velocity, just drifting with the Hubble flow. And then your wristwatch is the time that we will work with. That is, so we are talking about the proper time of an observer without peculiar velocity. With a very good approximation, that's actually your watch. The velocities that we're dealing with are, for example, the Earth is going like 25 kilometers a second. And then in the galaxy, you have like hundreds of kilometers per second. And then the speed with which Andromeda and Earth and Milky Way are approaching each other, I don't know, must be thousands of kilometers a second. But of course, if you have galaxies that are really far away from each other, then you can have much larger relative velocities. Because you can have redshifts of 2 or something like that. This corresponds to really large velocities. Now, what is the choice of space coordinates then? Well, it will be convenient to use so-called co-moving coordinates. And in order to construct a co-moving coordinate system, we proceed like this. We choose a time, it could be today, for example, and then we set up an ordinary rectangular coordinate system. So you take rods, and each one is a meter long, and you build a rectangular frame, and you do that for billions of light years across. So you have a coordinate system, and then your coordinates mean, 100 in the x direction means like 100 meters or so. But then the key with the co-moving coordinate system is that we let the co-moving coordinate system grow and shrink with the Hubble flow. So imagine that this coordinate system has rods that are flexible. Or in fact, they have to be motorized, I suppose, such that as the universe is expanding, the rods lengthen. So that the entire coordinate system made out of cubes, right? These cubes grow exactly with the Hubble flow. This is going to be a very convenient coordinate system, because in that coordinate system, if you look at a galaxy, it will have a certain triplets of coordinates in that coordinate system. And if the galaxy has no peculiar motion, it will keep those three numbers as its coordinates, right? Because it goes with the Hubble flow, but so does the coordinate system. So all galaxies are standing still with respect to the co-moving coordinate system, except that they might have peculiar velocity. But apart from that, they're just standing still there. And another advantage is that, so here I'm listing the advantages. One advantage is that anything that is just going along with the Hubble flow will be addressed in that coordinate system. But secondly, let us look at what happens with waves. If we have waves traveling in that space-time, like a plane wave, then its wavelength, physically speaking, its wavelength is going to increase because it's going to be stretched. As the universe underneath it is expanding, the wave will be having a larger and larger wavelength. That will also affect its frequency, but let's not worry about that. Consider just the wavelength of a wave traversing the universe. Over time, as the universe expands, the wavelength expands, but not in this coordinate system. Right? In this coordinate system, the wavelength of a wave stays the same numerically. Even though, of course, the physics being described is an expanding wave, numerically, the wavelength stays the same value. That is crucially important for what we are going to do next. Because remember, the reason why in quantum field theory it is convenient to work with the Fourier transform basis. The reason was that the Klein-Gordon equation, written down in space and time, has space derivatives in it, Laplacian, right? And those space derivatives meant that the harmonic oscillators in space are coupled to each other, right? The derivatives made them coupled, which makes sense because, you know, you put a charge somewhere and shake it, it will locally excite the field, but the excitation won't be confined to there, but instead the field will tickle the field further out, and that will tickle the field further out, and so you have a wave propagating away from wherever you shook the charges. But mathematically, that's a bit inconvenient because you have all those oscillators in the quantum field that are coupled to each other. So we changed to the Fourier basis, and we had then these Fourier modes, and we found that in the Klein-Gordon equation, the space derivatives became simple multiplication with the momentum. So a differentiation became a multiplication. And then we found that the Klein-Gordon equation in momentum space is just a bunch of ordinary uncoupled harmonic oscillators. So we were able to quantize them individually and so on. So that's very convenient. That's not to say that the picture of the harmonic oscillators that are coupled in position space is not important. It's very important. For example, it's important because the fact that the harmonic oscillators are coupled, the spatial harmonic oscillators are coupled, means that the ground state of the field is an entangled state. Whenever you have two harmonic oscillators and they're coupled, then the ground state is an entangled state. And that is the origin of entanglement entropy in quantum fields, and a lot follows from that. In fact, the entropy in a black hole may be entanglement entropy originating in that feature. But for the purpose of solving a quantum field theory, going to momentum space is the way to do it, because then you decoupled these infinitely many harmonic oscillators that used to be coupled in position space, make them uncoupled in momentum space. Now, when the universe is expanding, the Fourier basis is no longer good enough because wavelengths are changing, which means the harmonic oscillator of the mode of one wavelength might be excited now, but a little later it's no longer excited because now the wave is having a larger wavelength. So you can view the expansion of the universe as a handing down of excitation from the modes of a short wavelength to the modes of a larger wavelength to a larger wavelength and so on. We avoid all of this coupling in momentum space by choosing a co-moving coordinate system. We will see that in this case, by using the co-moving spatial coordinates, when we do the Fourier transform for this coordinate system, then we will get, again, uncoupled harmonic oscillators with all the benefits that come from studying that. So that's ultimately the reason why we want the co-moving coordinate system. Waves keep their wavelengths because they expand along with the Hubble flow, and so does our coordinate system. So they keep their wavelength, which is to say that the mode oscillators, there is one mode oscillator, one co-moving mode oscillator that describes the wave at all times because it follows it along. Oh, now again this adventure here. How do I do this? Ah, there we go. Okay. Then, what about the metric? Well, remember that the metric determines the line element, the invariant distance, in this way. That's the invariant for distance. In our coordinate system, the metric tensor must therefore be of this form here. Why is that? Well, there's a 1 here in the 0, 0 component, and that's because when we measure the proper time of somebody going along with the Hubble flow, that was our time definition, right? Then, well, it is the proper time, by definition. Which means that if we are not moving in space, if we're just measuring a time, well, we are measuring proper time. So it really, in this case, the ds squared is the dt squared, and there ought to be just a 1. However, if what we are measuring is a spatial distance, so we are measuring at equal time, but different spatial points, then we are measuring here ds squared, which is a spatial distance, a space-like distance. Then we get the dxi squared. And now the proper distance is no longer trivially related to the coordinate distance, because the coordinate distance grows over time. Right? So if you take 2 points in the coordinate system and you just let time pass, well, they move further and further apart from each other physically, even though mathematically they stay at the same point in the coordinate system, they physically move further apart. And that is encaptured by having here a factor, let's call it A of t, which takes care of that. So if you take the same coordinate distance here, same coordinate distance, at a later time or earlier time, it means a different proper distance in this calculation. So this is why there is a scale factor in here. And that is called the scale factor function. So what about this scale factor function? It will capture the expansion of the universe. It captures the factor by which the co-moving coordinate system has expanded or shrunk if you go to the past. So for example, if you take the proper distance between two galaxies, which have a co-moving distance, delta x1, delta x2, delta x3, so these are the coordinate distances in a co-moving coordinate system, then, and we do this at a proper time t, so at equal time, we look at where is this galaxy, where is that galaxy, and their coordinates differ by these amounts in the co-moving coordinate system, then the actual proper distance between them is given by, the square root of the invariant distance, where only the space components contribute because we do it at equal time, so there's no delta t here, no delta x naught. So we get the numerical Pythagoras distance in the coordinate system multiplied with the scale factor. So that's why the A of t is directly the amount of shrinkage or expansion of the coordinate system along with the Hubble flow. So what then is the dynamics of A of t? Well, easy to say. The function a of t, the scale factor function, is determined by all equations of motion. But literally all of them. And how is that done? Well, in principle, you have to do this. Consider the laws of nature as far as you know them. So you take all equations of motion, you take all fields, you consider all fields that you know of, and you calculate for all physical fields their contribution to the energy momentum tensor. The energy momentum tensor just additively collects contributions from each field. So you calculate the contribution to the energy momentum tensor from each field. Actually, it has contributions not only from the free actions of each individual field, there will also be contributions from the interaction terms between the various fields. So you really have to take the entire action of all matter and radiation and then calculate the energy momentum tensor from that total action. And in practice, this is not feasible. We will do that for the fields that we consider most important for cosmology. And as it happens, we are lucky. Apparently, a scalar field was most important in the early universe cosmology. And so we will get away with considering the energy momentum tensor of a scalar field, the inflaton field. Okay, so once we've done that, once we've calculated the energy momentum tensor of the fields that we care about, that we think are the most important in the context, once we have that, then we have to solve simultaneously the equations of motion for all the physical fields that are important in the setup that we consider, together with the Einstein equation for the metric. And the metric is just given by this. So it's the Einstein equation is really an equation for A of t. So we have to solve two sets of equations, the equations of motion for the field and the Einstein equation, where the Einstein equation is coupled to what the fields are doing. So unfortunately, we cannot just solve these and then independently of that, we solve the Einstein equation. No, they are coupled. The Einstein equation is here, and the curvature tensor is expressed, of course, in terms, I'm assuming you know these things, but I'm just summarizing them quickly. The Riemann curvature tensor and the Ricci tensor and the Ricci scalar are expressible in terms of the metric. So all of the left-hand side is a complicated expression in A, ultimately, in A of t. And the right-hand side has the energy momentum tensor that we just expressed in terms of the fields. So the goal is to solve the Einstein equation and all the equations of motion of all the matter and radiation fields. In cosmology, remember, radiation is not considered separate from matter. Even radiation is considered matter. Everything that's not gravity is considered matter. Now, in practice, we can't do this. We have some good ideas about how to solve the equations of motion for matter fields, such as fermions, photons, gluons, WZ bosons, neutrinos, and all the rest. But we don't know how to do the quantum theory of this. Now that poses a big problem because the two systems are coupled. The Einstein equation is coupled to the equations of motion for the matter fields, and we can put hats on this and work with the commutation relations for that and Hilbert spaces and all this, but the Einstein equation we can only solve, at least in some circumstances, in the classical scenario. So we have to do something to make the two equations compatible. And what is then often done is that we reconcile the fact that the left-hand side has to be number valued and the right-hand side is operator valued, because the energy momentum tensor really is composed of fields, quantum fields, which have non-trivial commutation relations. So to reconcile the fact that this is really operator valued, and this, well, is also operator valued, but we don't know how. We can only handle it number valued. We just put expectation values there, which will turn the right-hand side into something number valued too. That's the semi-classical approximation. So here the idea is that we will quantize the fields, the physical fields, the matter fields, but we will not quantize the metric. Later in this course, we will do a little bit better than that. We will actually quantize perturbations of the metric as well, but not for now. So we will quantize only the matter fields, but not the metric, in order to, if this is operator valued, this will be operator valued, in order to make that compatible with the Einstein equation, which on the left-hand side has only number valued stuff. We take the expectation value of the energy momentum tensor, simply like this, and then work with that in the Einstein equation. That's much easier said than done, because typically you get infinities when you calculate these things. It will be an infinite amount of vacuum energy, for example, and it requires some renormalization. But there is also a more fundamental problem with this, which is that what we're saying here is that we have an energy momentum tensor for every event in space-time, T mu nu of x, number valued. How can that be? Remember from first quantization, if we learned anything from first quantization, it is that energy and momentum cannot be localized, right? If you know where you are, you don't know what momentum you have. But this is saying that, you know, at every point in space and time, you're supposed to know what the energy momentum density is. And so something is going on here. This is definitely not how nature works. We can only view this as an approximation that we do because we can't do better. But it's definitely not satisfactory. In case you wonder where's curvature? Didn't we just say that in the Friedmann-Robertson-Walker model of the universe, there is no curvature? Space is flat. So why general relativity at all? Well, the point is that, yes, in a Friedmann-Robertson-Walker universe, we don't have spatial curvature, but we have curvature between space and time. And if you remember what curvature actually means that you do parallel transport in one direction, then in another direction, and then you go back closing the parallelogram, and you don't come back where you started. If one of those directions is time and the other is space, and you don't come back to where you started, what it means is that space has expanded or shrunk. So curvature in the space-time directions between space and time is really expansion or shrinkage. And therefore, the A of t is the A dot of t, the time derivative of A, is actually related to curvature between space and time. By the way, a notation that we're going to use is that the dot corresponds to differentiation with respect to time, to the proper time, and later we will also have a prime, which is a differentiation with respect to conformal time. It's another time variable. But for now, the dot is differentiation with respect to the proper time of somebody who's just flowing with the Hubble flow. Now, for now, just to get the hang of doing quantum field theory in curved space-time, we will assume that A of t is basically given. We will consider a situation where we know that the space-time is a Friedmann-Robertson-Walker space-time, given by a metric of this form, and we assume we know that it has a particular scale factor as a function of time, A of t. And then we will study a quantum field living on that background space-time. Basically, the assumption here is that whatever the quantum field does, it is not the reason for why the space-time is behaving the way it is. So we're just looking at a passenger quantum field, which is just riding along with the general Hubble flow that is caused by some other reasons. So we're just, initially we will just study quantum field theory on an expanding space-time that's given as a background. We are not looking at how the quantum field affects that background. We will do that later, but not just yet. And this, of course, will mean that we don't have to worry about solving the Einstein equation, working with the semi-classical approximation. No, we will just take a well-motivated scale factor function A of t, and we will say, how does a quantum field behave when this is how the evolution of the universe goes.
How do we determine the state of matter?
Yeah, well, yes, it's very difficult. Well, it's of course the state that the quantum field is going to be in. And that could be a state like the vacuum, but it might also be a state of a plasma. It depends on the physics behind it. The math can't tell you.
There is no preference.
No, we will spend quite a bit of time on determining what the state of a quantum field is going to be on a curved space-time. Yeah. And generally, if you start out in a vacuum state, it's not going to stay the vacuum state for long. Yeah. So it's going to be some excited state, and we'll have to see what it will be. But a common assumption will be that very early on, the universe might have been started out in a vacuum state. And for example, if you have a tremendous inflation, then no matter what the state was before the inflation, you would expect that all matter that there was before will be diluted enormously. Because if the universe expands its volume by a huge factor of 10 to the 10 to the 10 or something like that, then whatever matter there was before will be completely diluted. So you would think, okay, if the vacuum state is a good approximation for that. But then it may be repopulated by particle production through the expansion. And actually that's what we will find. We will find that the standard model of cosmology nowadays holds that our universe might have come from a mother universe that might have been complicated. But because of the huge expansion, whatever remnant matter there was is now, I mean, in the original patch that expanded so much, is now tremendously diluted. And all the matter that we see around us now was actually generated by the very expansion. So that's pretty nice, because it means that whatever there was before was kind of deleted or washed away. And then we get fresh matter content. Yeah. Okay. Now, yes?
Is that because you said recreation due to expansion?
Yes.
It's not the reheating part of inflation?
It has to do with that, yes. Ultimately, the inflaton potential, you see, remember the idea was that when the inflaton potential fluctuates upwards in a sufficiently large homogeneous patch, then it acts like a temporary cosmological constant that makes that little patch mushroom out into a whole new universe, right? And it started all when the inflaton potential was elevated. Now, 10 to the minus 29 seconds later or so, you have this entirely, I mean, very large entire universe having mushroomed out of that fluctuation. But the potential is still large. The potential has to come down eventually. And when the potential comes down, all that energy can go into the production of all kinds of particles. And that will do the reheating then. But there are other things going on as well. Non-adiabaticity of the evolution of the mode oscillators during that expansion. And that will create fluctuations which imprint themselves then on that reheating. And we'll do all of that in much more detail. Okay, so now we started with defining a time variable, which was the proper time of somebody flowing along with the Hubble flow, and the co-moving space coordinates. Now let's change our minds about which time variable to use. There is a more convenient time variable. And why is there a more convenient one? Let us look at the metric. So far, with the coordinates that we're using so far, this is the representation of the metric tensor. Wouldn't it be convenient if the metric tensor could be brought into a new form by change of variables, such that it actually becomes proportional to the flat metric? It can't be the flat metric, because otherwise space-time would be flat and we would be dealing with Minkowski space. But you see, it already has almost the shape of the eta of special relativity. It has here a plus sign and here negative signs. It's just that there are a's here, but there's no a over there. If there was an a over there, then we could just put this, I mean a squared, we could just put the a squared factor in front, and we would have just the eta matrix there. And if you suspect that having an eta matrix there might simplify things, you would be right. It will make a big difference. So yes, that is a convenient thing to have. The metric proportional to eta mu nu. But what do we need for that? We need to change coordinates in such a way that an a squared appears over here, so that we can pull it out of the metric, right? I mean, out of the matrix. It's still part of the metric, of course. But how do we do that? Well, this thing has to do with the time coordinate and only with the time coordinate. So if we change the time coordinate in a non-trivial fashion, then we can change this number 1. Let's change the time variable such that an a squared appears here. You can always do that. So what we need is, we need a new time variable such that this trivial calculation of the proper distance becomes a non-trivial one that involves an a squared. So we need that the proper distance squared is a squared times the change in the new time variable that we will call eta. So in differential, if we write that in a differential way, what we want is that scale factor times the eta, where eta is the new time variable, it's got to be dt. Then that will work out. So we can write this as a differential equation. So the new time variable differentiated with respect to the old time variable, so we have eta of t, it's got to be 1 over a. Right? So d eta by dt is 1 over a. We can integrate that. So we integrate both sides with respect to t, and then we get eta of t, that's just the antiderivative of this, right? And on the right-hand side, we have to integrate this over t. So we have to integrate from some starting time to t of 1 over a of t prime dt prime, where the starting time doesn't really matter. It's just ultimately the integration constant. And of course, the new time variable eta will only be unique up to a constant. Because if you add to the new so-called conformal time a constant, then it will not change that derivative. That equation will still hold, right? So now that variable will be called the conformal time. And why is it called conformal time? Well, it's because if we use this time variable, then the metric becomes proportional to the eta metric of special relativity with this prefactor a squared of eta. Now, I have to admit that the community is unfortunately using, and I'm using that too now, the symbol eta for two very different purposes. One is to use it for the conformal time, and the other is to denote the special relativity metric, right? But this thing carries indices, that thing doesn't, so hopefully there is no way to confuse the two. Okay, so now that we've changed to conformal time and co-moving spatial coordinates, the metric looks like this. So we might think, okay, that's perfect, isn't it? Now we can do everything. Oh, let's see, where are we? Okay, so the metric with two lower indices had an a squared here. The metric with two upper indices we will also need. And it has, of course, a inverse, a to the negative power 2. And remember why that is? It's because the metric with upper indices is literally the inverse matrix to the metric with lower indices. Therefore, since the G with lower indices has an a squared here, the G with the upper indices has a 1 over a squared. Right? We always have that. In whatever coordinate system you choose, that's always true. So in particular, this means that we can now calculate all the quantities that go into the action and that go into the equation of motion, because we have the metric. We need the determinant of the metric, we need the metric with lower and with upper indices. So in particular, for the measure in the integrals, we need the square root of the absolute value of the determinant of the metric. Okay, so let's look at the metric. We need to calculate the determinant of it. Well, what's the determinant of a matrix which has a squared up to minus signs? It has a squared on the diagonal only. So clearly, it's a to the 8th power. A to the 8th power is the determinant here. with a minus sign, but we take the absolute value of that. So it's still a to the 8th power. And then we take the square root of that. That gives us a to the 4th power. So whenever the square root of g comes up, this is what it's going to be in an FRW spacetime, a to the 4th power. Which is, quite plausible. It's just the space-time volume, right? The scaling of the space-time volume. That's what the square root of g is taken care of. And you see that the conformal time does what the co-moving coordinate system does for time. That's why you get that. Okay, so now we can do the Klein-Gordon field in FRW spacetimes. We will not introduce the potential for the Klein-Gordon field. Let's just look at the free Klein-Gordon field. Then the free Klein-Gordon field on a FRW background spacetime has this action here. In fact, on every spacetime, it has this action. Remember, that's just the formula that we had earlier. So this is the covariant square of the derivatives. That's the D'Alembert operator here. It's minus the D'Alembert operator. And here 1/2 m squared phi squared. And the measure factor. Now, let's spell out what that is on FRW spacetimes. Here we have a g with 2 upper indices. If you remember, that was the special relativity eta matrix multiplied with 1/a squared. And then we have here those 2 derivatives. And we know, of course, already how this is going to play out, right? That's a d phi naught squared and the Laplacian. And here we have this. And then the square root of the absolute value of the determinant of the metric is just a to the 4th power. And we have to remember that this x are the co-moving coordinates, and this is the conformal time. So now we have the action, and everything looks quite doable. We can now calculate either directly from the variational principle that of what the equation of motion is, or we can go back to the general Klein-Gordon equation for any space-time, and then plug in again what the g is and so on, and then find out what the Klein-Gordon equation is. Oh, let's see. All right, so that's where we were. Okay. So here we have the general Klein-Gordon equation. Now let's plug in the values that we know. This is a to the 4th power. So this is 1/a to the 4th. This is 1/a squared times the Minkowski metric. Here we have a to the 4th power. Yeah, and that's it. So let's see what we get. Here we go. You see it's the 1/a to the 4th power, and the Minkowski metric, a squared, and right, that's what we get. Now, let's work that out. What is the Klein-Gordon equation explicitly when we spell out all the sums here? We're going to have 2 terms here, 2 kinds of terms. See, this derivative doesn't commute with these terms, but it almost does. By the Leibniz rule, the derivatives are going to just combine with this in one case, but in another case, the time derivative in here will act on that. Okay, so by the Leibniz rule, let us first consider the term where this is not differentiating the a of t, the a of eta. Then what do we have? We have 1/a to the 4th. We have the eta carried forward. We have the a squared carried forward because we're not differentiating with respect to its dependence on eta. And then we just have these partial derivatives contracted with the Minkowski metric. And then we get the extra term where, by the product rule, where the d by dx0, which is d by d eta, is acting on that. Okay, so we carry forward the 1/a to the 4th power, And then we have the time derivative of this, which gives us a 2a prime a. Now the prime denotes differentiation with respect to conformal time. Dot would have been with respect to the proper time. Okay, so it's 2a prime a, that's the eta derivative of that, and then only one derivative left over. It's only the d by dx naught because this thing is diagonal, right? Okay, plus m squared just carried forward. That's the Klein-Gordon equation here. So everything written up again now multiplied through with a factor of a squared. See, here we have overall 1 over a squared. And if we want to get rid of that 1 over a squared preliminary factor, we can do it by multiplying the entire equation with a squared, which is legal because a is not going to be 0. Universe is not 0 size. So what we get is second time derivative, conformal time derivative. That's this term here from that. You see, this is just the D'Alembert operator. And here's the second part of the D'Alembert operator, the spatial derivatives in here. And then this is carried forward like that. Instead of having 1 over a to the third power, because we multiplied the whole thing with a squared, we are just left with a prime over a. That's this a prime over a. And then since we multiplied the entire equation with a squared in order to get the a squared over here rid of, so we get an a squared times m squared here as well. So this equation is that 1 times a squared. Okay, so here we go. That's the Klein-Gordon equation for FRW spacetimes. But is that the thing you want to quantize? It's not. There is a problem with it, which is that it introduces an element that we have not studied before. Let us look at the shape of this thing. This Klein-Gordon equation has roughly this form. A double prime plus something or other multiplied with phi prime. And phi double prime plus something phi prime plus something phi equals 0. That's no good. It looks like a harmonic oscillator, all right. We have the phi double prime here and the phi. But what about this thing here? It's a first derivative. If we encountered that in classical physics, we would say it's a friction term, right? Or anti-friction, depending on the sign. And usually when you have that, you ought to couple to another system and see where the energy goes. And, it's just something we are not so familiar with. Not that we couldn't handle it, but, it's not something we are familiar with, and we can avoid it. We can avoid that term quite easily simply by yet again changing coordinates. But in this case, we are not, I shouldn't say changing coordinates, it's changing variables. Now, we stick to the conformal time. We stick to co-moving coordinates because they are just so convenient, because everything is just conformal to the Minkowski metric, just multiple, time-dependent, but still multiple of the Minkowski metric. No, what a freedom that we haven't used yet is that instead of working with phi, we might work with a function of phi. We might work with a different variable. Instead of choosing phi as the basic variable, we choose some other expression in terms of phi as the basic variable. And if we choose that cleverly, the new variable, maybe then that very same equation takes a more familiar form, hopefully that of some sort of coupled harmonic oscillators without the friction term. So, let's see. Here's the strategy. We will use a new field variable. Instead of phi, we will use chi. And the chi needs to be chosen cleverly. We will choose a field variable chi so that the equation of motion for chi has no friction type term, which is to say no term that's proportional to chi prime. Let's keep in mind we're going to solve the same old equation. We're just doing it in a slightly different set of coordinates. And it turns out that we don't have to look very far. This simple ansatz will do already. We could derive that ansatz, but it's easier if I just tell you what the solution is and we verify that it's really working. So the claim is that if instead of working with the field phi, you work with A times phi, the rescaled field phi, So you work with a field chi, which is the rescaled field phi, with a cosmic scale factor, then the claim is that the equation of motion for chi is going to be of the more familiar kind of coupled harmonic oscillators without a friction term. Let's just quickly anticipate what we might expect for this chi. See, the universe is expanding. The scale factors A of eta that we'll be working with will reflect reality. In other words, this thing blows up without bound. So what that means is that if phi behaves reasonably, chi will blow up. Okay? So we should expect that chi will blow up, and that doesn't have to mean anything that this blows up, physically speaking. If chi goes to infinity, if sort of the expectation values of chi were to go to infinity, for example, or even if the fluctuations and so on, if things to do with chi go to infinity for late times, that's not necessarily a bad sign, because even if this thing behaves reasonably, the scale factor blows up, right? So let's keep that in mind. All right, so with this new set of variables, the chi of eta and x, so the chi is a field depending on the conformal time, co-moving positions, simply the old variable phi that we're really interested in, multiplied with the cosmic scale factor. Well, then what do we have? Well, it's calculated. What is phi prime now? Well, phi prime is the eta derivative, by definition of what the prime means. It's the eta derivative of 1 over a chi, right? Because phi is chi over a. So it's this. If we spell it out, we obtain that this is minus a prime over a squared chi plus 1 over a chi prime. And if you play around with it, you will see that this is the key. Now, let's continue with this. What does the... So we just calculated what the time derivative of phi is in terms of the new field variable. It's this. Now let's find out what the space derivative is of phi in terms of the new variable. And that is trivial to calculate because the spatial derivatives commute with the scale factor. It's only dependent on time. So therefore it's just space derivative, right? So the space derivative of phi goes into the space derivative of chi, keeping in mind that chi and phi differ by the scale factor. Okay, so now we can express the time derivatives and the space derivatives of phi in terms of chi. And that's all we need in order to plug it into the action, plug it into the equation of motion. And so in particular, it's now a simple exercise, and I leave it to you as an exercise to do this, to re-express now the Klein-Gordon action. Remember, same action, didn't change it. We just changed the way we write it. If we write the Klein-Gordon action no longer in terms of phi, but in terms of chi, then this is how it looks like. And what we see here is that we have basically a D'Alembert operator as if on flat space now, and we have basically a time-dependent mass term. By the way, maybe we should quickly go back and look at the Klein-Gordon equation. Yeah, we didn't really spell it out. But in any case, you know, from here you put in the definitions, and then you get from here you put in the definition of what chi is in terms of phi and the derivatives, and then you can work out what the action is in terms of chi, as I just claimed. But remember that if you express the Klein-Gordon action in terms of phi, you notice that the D'Alembertian part is still decorated with an a squared factor, right? That this was ultimately giving rise to the friction term and these things. Whereas now here in the here's the friction term, and then we are here now, And you see there is no measure factor, there is just no scale factor here. This is really just like the ordinary flat space Klein-Gordon, just the sum of plus the second time derivatives minus the second space derivatives. If that wasn't there, it would be just a free massless Klein-Gordon field in special relativity, right? In Minkowski space. And then we also have this term here, and if A was independent of time, we would just have the ordinary Klein-Gordon equation on flat space, on Minkowski space. But it's time dependent. And we also see this funny term. And what will be very important later on, what may be the reason, what may be the origin of us, of quantum fluctuations that gave rise to us, may be the difference in the sign between these two. That may be the most important sign difference ever, anywhere. And the reason is that so far, this is just regular physics. It's just going to be a regular harmonic oscillators. But because this thing comes with a negative sign, you can have that this thing dominates over that, which turns harmonic oscillators from this way to that way. And that allows quantum fluctuations to be amplified. All right, but we'll get more of that later on, of course. So then this is the action in terms of the chi field. What are the equations of motion? First of all, let's ask, does it matter whether we work with phi or with chi? If we calculate the equations of motion this way, ds by d phi is equal to 0. Could it be that we get a different equation of motion than if we do it with this, ds by d chi equal to 0? Or do they lead to equivalent equations of motion? Well, it's going to be the same, and you can see it this way. You see, if 0 is equal to ds by d phi, well, ds by d phi is ds by d chi by d phi. So if this is not 0, then, and it isn't, because we know what it is, right? It's just a squared. Just a, actually. So that's not 0. And that means that this is vanishing exactly if that is vanishing. Right? So it doesn't matter which one of the two Euler-Lagrange equations we use. So we might as well calculate the Euler-Lagrange equation directly in terms of chi from S of chi. And when you do that, and I leave it to you as an exercise to do this little calculation, just take the Klein-Gordon action in terms of chi as we had it just previously. It takes this very nice simple form. Then this is the Klein-Gordon equation that you get from that action, as was predictable. You see, we had the regular D'Alembert as if it was on flat space, but the mass term consists of two terms that are time-dependent and with opposite sign. So that's the Klein-Gordon equation now. That's our equation of motion 1. And there are two ways to obtain it, right? You could just take the Klein-Gordon equation in terms of phi and translate it by changing the variables. Or you could change the variables in the action and then do the Euler-Lagrange equation for the action in the new variable. We just proved that both paths give you the same outcome. Now, let's prepare for quantization. In order to quantize the theory, we need not only phi, well, or chi, we also need its canonically conjugate momentum field, so that we know what to impose canonical commutation relations with. Now, this is where it gets quite subtle. You see, the phi field has a canonically conjugate field. Let's call it pi superscript phi. But the chi field also will have its canonically conjugate momentum field. In each case, obtained from their respective actions, from their respective Lagrangians, by doing a Legendre transform. Let's see, are they the same? Do we get the same quantization? Do we get the same theory? So, let us consider the Lagrangian. First, we will just naively go about and calculate it for chi. So we work with the variable chi, and then we calculate what the canonically conjugate momentum field pi superscript chi is. right? So that's the canonically conjugate field to chi. Here's how we calculate it. We look at the Lagrangian of the theory. Remember, it's simply the action and you drop the time integration, right? So this is just a d3x. If it was a d4, we would have the action. So we have here the Lagrangian of the Klein-Gordon theory when expressed in terms of chi. We need to do the Legendre transform with respect to the time derivative of chi. Right? Because this is going to be the Legendre transform partner of chi prime. In Minkowski space, it would be chi prime again. But as we found out in several lectures by doing these things very carefully, in general, that's not so. So we wouldn't expect it here either. So what is the canonically conjugate momentum field to chi? Well, we need to do the Legendre transform with respect to chi prime. So we calculate the new variable is dl by d chi prime. And what is it in this case? Well, we are lucky. It's chi prime again. And the reason is that all the non-triviality, because of our choice of coordinates, choice of variable, all of the non-triviality is packaged in here. But these terms unaffected. They're just like in Minkowski space. So very conveniently, the canonically conjugate momentum field to chi is just chi prime as if we were on Minkowski space. So here we have our two equations of motion. We have the we have the Klein-Gordon equation, and that was the first equation of motion. The second equation of motion is this, the relationship between pi chi and chi. Now, for comparison, for completeness, let's calculate what is the field that is conjugate to phi. What's the pi superscript phi? In this case, we take the Klein-Gordon action expressed in terms of phi, strip the time integration, the eta integration, then we are left with the Lagrangian. And then we functionally differentiate the Lagrangian with respect to phi prime. And what is it going to be? Well, it's not going to pick up anything here, and here this is diagonal, but it's going to pick up the a to the minus 2. Together with the a to the 4th is a a squared. So what we find is that the pi superscript phi is a squared phi prime. Somewhat non-trivial here. So let's compare. We have a canonically conjugate momentum field to chi, which is chi prime, and we have a canonically conjugate momentum field to phi, which is given here. Let's compare. So this is chi prime. Chi prime is a times phi prime, because chi is a times phi. So let's work that out. Well, we get it's a times phi prime by the product rule plus a prime phi. And that is 1 over a pi pi superscript phi plus a prime phi. Right? So why is that? It's because the phi prime is up to a factor of a squared, the pi phi. Right? So here we have an a, but we have to accommodate that factor of a squared, so we get the pi phi here. So definitely, we have that the canonically conjugate field to chi is not equal to the canonically conjugate field to phi, and more than that, it's also not equal to it up to a scale factor 1 over a, right? So phi and chi are related by just a scale factor, but the canonically conjugate momentum fields are not related just by scale factor. They also have this extra inhomogeneous part there. So they really are different. Now, how do we quantize? Well, we quantize by imposing the canonical commutation relations between phi and pi, of course, because these are the fields we really care about. These are the physical fields. The chi is just a convenient variable. So we impose these commutation relations where the pi here has a superscript phi. These are the commutation relations. Now, in terms of the fields chi and the canonically conjugate field to the chi, the pi superscript chi, these commutation relations become what? Do they become funny looking or what? No, they don't. They become just what we might have expected or what we might have hoped. They are still of the usual kind. And the reason is ultimately that we have these scale factors. I mean, chi is related to phi by a scale factor, but also the pi is related to, the two pi's are related by a scale factor, which is opposite, and the two scale factors just cancel each other. And then we also had this extra term, if you remember, this inhomogeneous term that was annoying. But it's a term that doesn't contain the pi in it. And so it commutes and it doesn't disturb it. Okay, so these are the commutation relations to impose here. But, you know, it would be best if you just verified yourself. Oh, sorry. I have the solution here. Okay. So let's check the first canonical commutation relation, for example. So we have the chi with its canonically conjugate momentum. We spell it out. The chi is a times phi. The pi chi is, as we just calculated, this expression plus the inhomogeneous term. And this term has a phi in it, which commutes, of course, with that phi. So that's why the inhomogeneous term is not messing up the commutation relations. And then this term and that term have scale factors that cancel each other. And we're left with just the commutator between phi and pi phi. And we know that that is the canonical commutator. And so the chi and the pi chi also have the canonical commutation relations. So that would have been the exercise. Okay. So now we conclude that changing variable from phi to chi is not so bad. It seems that, you know, quantization is fine, and we only get benefits by doing that. However, there is something non-trivial going on here too that we should clarify. Namely, imagine we start out with a Lagrangian, and remember there is just one Lagrangian. I mean, there's one Klein-Gordon action. 1 second, please. There's one Klein-Gordon action. We drop the time variable, then we have one Lagrangian. We can write it in terms of this variable or that variable, right? But it's one Lagrangian. But if we write it in terms of one set of variables, then the Legendre transform gets us to one Hamiltonian. If we write it in terms of other variables, then the Legendre transform will get us to another Hamiltonian. We'll have to discuss whether or not they are the same. Ahmed, you had a question?
Yeah. So it seems like basically we're just lucky because of the way the Friedman-Robertson-Walker metric was, that we were able to get this new chi that gives us Klein-Gordon-like equation.
That's right.
And it also gives the commutation relation, so we can do the Fourier transform.
We were excessively lucky, that's right.
So this is not a method we would apply in a different context.
Yes, that's right. Yeah, it's not a general method, yeah. From that, you cannot conclude that you can do the same thing with black holes, for example. Yeah. Rotating black holes. Okay, so let's address the following question. When we start with the unique action, we get a unique Lagrangian that may be written in terms of different variables. But here, we part ways. You see, if we do a Legendre transform of the Lagrangian, where we do the Legendre transform with respect to the variable phi prime, then we get some Hamiltonian. If we do it with respect to the variable chi prime, we get another Hamiltonian. In principle, those two Hamiltonians have no reason to agree with each other. So what's going on? And in particular, what does that mean? Which one is the energy? You see, there can only be one energy. You see, energy curves space. In general relativity, it matters what the energy is. You can't even just add a constant to it. That will already have an impact. Here we're talking about really different Hamiltonians. So which one is gravitating? which one is the energy, and which one is generating evolution in time, which one is the generator of evolution in time. Now, the last thing we can answer right away, because remember that what the Legendre transform does, it simply transforms the equations of motion into a new formulation. And it doesn't care what the physics of it is. So we know that this Hamiltonian will succeed in generating the time evolution, so will that one. Both will be generators of time evolution. They just do it a little differently, and I'll show you in a moment how they do it differently, but they both do it. But we'll also have to ask which one is gravitating. Okay. So first of all, how can both be valid generators of time evolution? Keeping in mind that they will both be valid generators of time evolution by construction. The Legendre transform will not fail us. So how can it be that we have that the time evolution of phi, so phi prime, is the commutator of phi with h phi, and the time derivative of chi is the commutator of chi with h chi? How come that how do they know which Hamiltonian they have to commute with in order to generate their time evolution if the two are not equal? Shouldn't there be just one Hamiltonian for all variables? Yes, indeed, there is in principle one preferred Hamiltonian for all variables, and that Hamiltonian is of course the original one, h superscript phi. You can still use the other one too, but this is the primary one, and here is how it all resolves. Remember that in quantum mechanics, when you calculate the Heisenberg equation of motion, and you have an observable of which you want to know its equation of motion, then the Heisenberg equation of motion says that the time derivative, I times the time derivative, is given by the commutator of your observable with the Hamiltonian, well, plus possibly an extra term. And that extra term arises if your variable has an explicit time dependence too. That is not just due to time evolution of the system, but due to the definition having time in it. Then you get an extra term here, right? So here we have that the chi is a variable that has an extra time dependence in it, right? And so on one hand, we have that the equation of motion holds true, that phi prime is given by, well, it's time evolved by the h phi. But if we spell it all out, if we write out what that actually is, so we have the phi prime here, then we have this 1 over a chi prime, because phi is 1 over a chi. Then we get 1 over a chi, commutator with this, right? And we can spell out what this is, and it gives us two terms. We will get one term where we differentiate the chi, and that's this one, leaving the 1 over a the same. And another term where we differentiate this thing, we get a prime over a squared, and this thing undifferentiated, and that. And you see that this term now can be moved on the other side. And so you see how the chi prime, how the chi field can be time evolved according to its own Hamiltonian without an extra term, or it can also be time evolved by the universal h superscript phi, by the proper Hamiltonian, where we are not using any fancy variables. But because the chi has a time dependence built into it, we have an extra term emerging here, and that's what that does. Okay. So basically, the message is that everything is time evolved by h phi, but you can also time evolve things with respect to the h pi, but you have to take care that you don't miss those extra terms. Okay, so since we have that chi prime is given by this, we know that from the general properties of the Legendre transform. And since the chi prime is also, as we just derived, evolving like this, we can tell by comparing that, you know, this must be equal to that. So in particular, the two Hamiltonians cannot be the same. If they were the same, right? So we just proved without calculating the Hamiltonians that indeed there are two Hamiltonians in the game. The h superscript phi is indeed not equal to the h superscript chi. But we also know now why this is not a problem. Now, that was the issue of the dynamics. And we resolved it, yes, both Hamiltonians are generators of the time evolution, just have to be careful about the Heisenberg equation, to take into account that variables might be time dependent explicitly as well. But now let's ask, since there are multiple Hamiltonians, in particular two Hamiltonians, which, if any one, is the energy? And by that I mean, is gravitating. Now usually we define, in ordinary non-gravitational physics, one defines the energy as the generator of time evolution. As we just did too. Both qualify as generators of time evolution, but they're not equal. So the definition of energy as the generator of time evolution breaks down at this point. We need another definition of what the energy is. Therefore, we follow Einstein here, and we define the energy momentum. We define energy no longer as a scalar. We define energy as the T00 component of the energy momentum tensor. And the energy momentum tensor is, following Einstein, calculated not by Legendre transform from the action, which would run us into this ambiguity, but instead the energy momentum tensor is calculated as the functional derivative of the action with respect to the metric. On flat space you get the same thing. But on curved space this is much better. So following Einstein, we consider the energy to be the 0,0 component, the energy density to be the 0,0 component of the energy momentum tensor, and in particular the energy is then the integral over all of space of the energy density. That's the total energy, and that is what you might then want to call the Hamiltonian. It's the total energy at a given point in time, so you take the energy density and integrate it over all of space. So here's the Einstein equation. On the right-hand side, the energy momentum tensor. On the left-hand side, the curvature. And it really matters what T naught naught is, what the energy density is, because any little bit of it will contribute to the curvature. So we can't have ambiguity in this. Now, for a Klein-Gordon field, we can calculate the energy momentum tensor. And those of you who've taken my course last term will remember it, I hope. The energy momentum tensor for the Klein-Gordon field comes out to be this expression. I mean, this is the definition. The energy momentum tensor for any kind of field is given by the functional derivative of the action of the field with respect to the metric, and then you multiply with 2 over the square root of the absolute value of the determinant of the metric. That's the definition of the energy momentum tensor. And when you calculate the energy momentum tensor for a Klein-Gordon field from its action through this functional derivative, this is the expression you obtain. It's quadratic in the field derivatives, and it also has a term that's quadratic in the field itself. And in particular, it has a well-defined 0,0 component. And that 0,0 component, so if you set mu equals 0 and nu equals 0, that 0,0 component is the energy density. So at a given point in time, given point in space, that's the energy density. And concretely, it is this. If you just plug in FRW space times metric, then with all the a to the 4th powers and stuff like that, then, and that's not difficult to check, you can do these few steps in a minute, and you find that the T naught naught, the energy density for a Klein-Gordon field, is given by this expression, 1 over a to the 4th power, 1/2 pi of phi squared plus these expressions. So I leave it to you as an exercise, and that will be the last thing today. And as an exercise to verify that this is the energy momentum tensor's 0,0 component for a Klein-Gordon field, and then for comparison, calculate what h superscript phi is. So carry out the Legendre transform that we talked about earlier. So you take the Lagrangian of the Klein-Gordon field, and then do the Legendre transform with respect to phi prime, get the Hamiltonian. Then compare the two. Compare T00 with h phi. And in this way, you should be able to show that if you take the energy density of the Klein-Gordon field and you multiply with the scale factor, I mean with the usual measure of integration, and you integrate over all of space, so then you go from the energy density to the total energy in the field, that expression is actually the Hamiltonian that you get in this way. So things are consistent. The Hamiltonian that you get by Legendre transform, directly from using the field variable phi, the physical field variable phi, will give you the 0,0 component of the energy momentum tensor, as it should be, otherwise you would be really in trouble. And for comparison, calculate the h chi. It's also a valid generator of time evolution with a bit of caution, but it's not having that interpretation. So the real energy is in h phi. Okay, I think that is that's all for today. Any questions? Yeah?
What if we had formulated the Klein-Gordon action in terms of chi instead of phi?
Oh, we did.
And then follow the same procedure here.
Yes.
To get the energy momentum tensor, I mean, in the functional differentiation.
Uh-huh.
So we express S the Klein-Gordon action in terms of chi, and then
We would still get the same thing though, because we take the same action and do the same functional derivative. So we should get the same T naught naught, the same T mu nu and the same T naught naught. We're not changing it. Remember that the action is the same. The action is the same no matter which variables you choose. The Hamiltonian is the thing that differs.
because we're doing the functional differentiation with respect to the metric.
To the metric, yeah. If we did a functional differentiation with respect to some decorated metric, yeah, we would get something else. Mm-hmm.
So we are basically doing a change of coordinates system. Basically, we just change the coordinates. We go from phi to chi.
I wouldn't call it coordinates, right? It's a different variable. Instead of phi, we use chi. You cannot absorb that by diffeomorphism on the manifold. It's not that you go from x eta to x tilde eta tilde or something. Yeah. So it's not a diffeomorphism, but it's kind of change of coordinates, but it's in the target space, right? It's in phi.
So I'm wondering about this friction term that is due to curvature.
Yes, due to the expansion.
So this chi field basically expands the Klein-Gordon field when the universe expands. 8 times 5.
Yes, that's right.
So I'm wondering what's the, I'm trying to understand.
Yeah. Okay, here's the intuition for it. As we will see later, the intuition that comes out of it is this. When you're looking at a wave propagating in space-time, then it has a certain wavelength, and as the universe is expanding, that wavelength is expanding along with it, right? And clearly, the wavelength also determines what the oscillation frequency in time will be. Now, something special happens when the expansion of the universe is so dramatic that the horizon exists on the space-time, which means that you can't communicate over distances larger than such and such horizon distance, right? And during inflation, the universe is expanding in an accelerated fashion, and if it is accelerated, the expansion, then there is going to be a horizon. And something special happens when the wavelength of a wave becomes larger than that horizon. Because then, not only will the wavelengths get larger and the oscillation frequency smaller, no. As soon as the wavelength is exceeding the horizon size for the expanding space-time, the oscillation will actually stop. And just the evolution of the field really will stop. And so it basically freezes the wave. It oscillates happily along, but then it slows down, and as soon as the harmonic oscillators go from here to there, that is the same moment in time as when the wavelength starts to exceed the horizon length, then the evolution will stop. Now, originally the Klein-Gordon equation implements that by something that looks like a friction term. The friction takes overhand, and it kills the dynamics and freezes the field, right? Now, what we do is that we get rid of that friction term by basically boosting the field so that the field will not freeze, but instead it keeps evolving. But the only way that it evolves is that its amplitude just keeps growing along with the scale factor. So in this way, we keep having the field evolving, just to avoid to have a friction term. And then later, of course, when we are interested in, when we harvest the physical predictions, we will go back to the field phi. So we will find that the chi field explodes, because as the scale factor grows, so does the chi field. But then we have to divide by the scale factor again, and that's when we will find that the phi field is sort of freezing in its track, as its wavelengths are exceeding the horizon size. Now, of course, we are not going to be so much interested in the actual values of phi. We are going to be studying the fluctuations of phi. And the fluctuations are following a similar scenario where they sort of freeze. As soon as the wavelength is larger than the horizon length, the quantum fluctuations freeze in their size.
So basically, the existing of a horizon give us that friction term. Because
Yes, that's right. Yes.
Even though we don't have it.
Well, that's right. And even before you quantize it, in principle, and I've suggested to some experimentalists to do this, and they seem to be keen on that. Well, I hope. I mean, I don't say keen, but open to the idea. In principle, even if you have a classical wave, it could be water or air, and you can arrange that the background water or the background air has a horizon. Then, if you have a wave on that, you should be able to see it freeze as its wavelength exceeds the size of the horizon. It should be a classical phenomenon too.
Yeah. Okay.